Determine the oxidation state of hydrogen in the reactant and the product side. Based on your answer, is hydrogen oxidized or reduced? All right, let's take a look. So, right over here, this is hydrogen in our reactant side. This is hydrogen in the product side. Now, hydrogen for the product side is pretty simple. Oxygen has oxidation state of -2. All right. Now, hydrogen has an oxidation state of +1. When hydrogen is bonded to a nonmetal, it's going to have an oxidation state of +1. When hydrogen is bonded to metals, that's when the oxidation state is -1. In this case, because oxygen is a nonmetal, it's +1. This also makes sense because you have two hydrogens, right? You have two +1 charges, right? So you have two hydrogens, each with a +1 charge. Therefore, the net charge for the hydrogen is a +2 charge. The oxygen has a -2 charge, right? So +2 -2 gives me 0. And this 0 basically indicates that this water molecule right over here is neutral. And it is, right? It has a charge of 0. So this makes sense. So hydrogen has a +1 charge in the product side, and also has a +1 charge in the reactant side, because notice how all the hydrogens here are just bonded to nonmetals, right? Carbon's a nonmetal, oxygen's a nonmetal. So yeah, hydrogen in this case also has a +1 charge. Also, another way to think about this is carbon and oxygen is more electronegative than hydrogen. So what it's going to do is it's kind of going to hog hydrogen's 1 electron, right? For this OH bond, if I were to draw this OH bond, hydrogen, recall that hydrogen shares an electron with oxygen. However, it's going to be shared unequally because the oxygen has a higher electronegativity. Thus, it's sort of like the hydrogen has 1 electron stripped away from it, even though it's sharing, right? Because it's sharing unequally. So it's sort of like it gained a positive charge, since it's kind of like it lost the electron because the electrons like oxygen more. So you would actually say for this answer that hydrogen is neither oxidized nor reduced. Neither oxidized nor reduced. Okay. I'm too lazy to write that, so there we go. In a lab experiment, you have this much CO2 gas from the completed combustion of propanol at this, so it's referring to this reaction right over here. We're still talking about it. Calculate the number of moles of CO2 produced. So we're given volume, we're given temperature, we're given pressure. If we want to calculate moles, PV equals nRT, right? We're just going to use the ideal gas law. It's important to point out that for the ideal gas law, the temperature has to be in Kelvin. All right. So in this case, we have our temperature in degrees Celsius. So what I actually have to do is I have to add 273 to this, and I get my temperature in Kelvin. So this is going to be 298 degrees Kelvin. All right. Whenever you want to convert from Celsius to Kelvin, just add 273 to the Celsius amount, and you get it in Kelvin. Now, if we want to solve for moles, if we divide both sides by RT, we're going to get the amount of moles is equal to PV over RT. So pressure is 1.10 atms. Volume is 27.0 liters. Divided by R, that's our universal gas constant. That's about 0.0821. Should be liters times atms divided by moles times Kelvin. And we have our temperature. So our temperature is in the denominator, right? It's RT, and it's 298 degrees Kelvin. Okay, and that's going to be equal to the number of moles we have. ATMs cancel out, liters cancel out, Kelvin cancels out, so we're just left with moles, which is what we want. So if I put all of this into a calculator, so 1.1 times 27 divided by 0.0821 times 2, that, I'm going to get approximately 1.21. Actually, let me see. Okay, everything has 3 sig digs, so I'm going to round to 3 digits. So 1.21 moles of CO2. And that's going to be my answer. It's important to point out that a lot of you guys might be saying, oh, can't we just take this 27.0 liters and we multiply it by So we have 27 liters of CO2. Now there is a conversion factor that relates liters to moles. All right, it's a very specific conversion factor. It's that 1 mole of gas counts for 22.4 liters for the volume. All right. However, this conversion factor only works at STP. This conversion factor only works at STP. Remember that STP is just when the pressure is 1 atm and the temperature is 0 degrees Celsius. So this conversion factor only works when the conditions are at STPs. But notice how our conditions are not at STP, so we can't actually use this conversion factor. Now, funny enough, if I actually do use the conversion factor, you do get an answer that's similar to 1.21. So that's pretty funny, but that's just like a coincidence, you know. And just take into account that this conversion factor, 1 mole of gas takes up 22.4 liters. This only works at STP. All right, once again. Using your answer to part B, calculate the mass of propanol that was combusted. And the molar mass of propanol is 60.1 grams per mole. Okay, for this, we have to use something called the mole ratio. All right, now we produced 1.21 moles of CO2. 1.21 moles of CO2. Now, for my reaction in this equation, notice how in order for me to produce 3 moles of CO2, I need 1 mole of propanol, right? So for every 1 mole of propanol, sorry guys, it's gonna produce 3 moles of CO2. All right, so for every 1 mole of propanol you have, it's gonna produce 3 moles of CO2. So in this case, if I have 1.21 moles of CO2, that means I'm going to need 1/3 the amount of propanol in order to produce that, right? So if I multiply 1.21 by 1/3, right, because I only need 1/3 the amount of propanol to produce 3 times the amount of CO2, I'm going to get 0.4333. It just keeps repeating. And then moles of propanol. Now we're not done yet because this is asking us for the mass. Remember, mass is in grams, and it gives us the molar mass, right? So what we have to do is I'm just going to multiply this by the molar mass. I'm going to say 60.1 grams of propanol. There's going to be 1 mole of propanol. The moles cancel out, and if you put this in your calculator, you should get this is around. So everything we round to 3 sig digs, right? We start out with these 3 sig digs, so I'm just going to round to 3 sig digs. 24.2 grams of propanol. That's going to be my answer, all right? So for some of these problems, you do have to use mole ratios to convert between moles of CO2 to then the moles of whatever reactants you have, and then convert it back to grams. Calculate the total amount of heat in kilojoules released by this combustion. All right, okay. So it says my delta H right over here, right? For this thing on top, it says my delta H value is negative 2020 kilojoules per mole. Okay, that's interesting. Now, sometimes you'll find the units for the heat of a reaction. This is the change in enthalpy, but this is also sometimes known as the heat for your reaction. And because this is a negative value, you're releasing heat, so this is an exothermic process. Sometimes you'll see the units for delta H be moles of reaction. Sometimes you'll just see it as kilojoules per mole. Kilojoules per mole of reaction, kilojoules per mole, or you'll just see it as kilojoules. But this kilojoules per mole right over here is very convenient, all right? This right over here, this right over here is basically saying it releases for negative 2020 kilojoules of heat for every 1 mole of this reaction, all right? 1 mole of reaction kind of just means that the reaction only occurred once, as you know, seen in this balance equation, right? 1 mole of a reaction just represents sort of just one of these reactions, right? Just one of this reaction right over here. Now, notice how, so right over here, we said how we needed, we had this many moles of propanol. All right, so I'm going to use this from part C. So 0.4033. And this continues, and We have moles of propanol. Okay, so I just used the information from part C because we already calculated this, but we said how we had 0.4033 moles of propanol, right, in my reaction. Now I can use a conversion factor, right? If you notice, in order for me to get this much heat, I need to combust 1 mole of propanol, right? So if I have this much heat right over here, that means that I combusted 1 mole of propanol. That's all that means, right? It's sort of like a mole ratio, except you're linking up the heat of the reaction to how much you actually combusted. So you can say that when you combusted 1 mole of propanol, you get, when you combust 1 mole of propanol, you get this much heat, negative 2020 kilojoules, right? So notice how moles of propanol cancels out, and you just get kilojoules, right? Which is the unit that we want because we are doing heat. So let me just once again just put this in the calculator. I get negative 815 kilojoules. Okay, so I get this much kilojoules of heat released. Next problem. The reaction occurred in a sealed calorimeter containing this many grams of water initially. Assuming all heat was absorbed by the water, calculate the final temperature of the water. Okay, so what's basically going on here is, imagine if you had like a sealed calorimeter. This is not a good diagram, but let's just say it like happened in a cup. All right, let's just say we had water, and let's just say we had some propanol. I'm just going to do it in yellow because fun color. All right. Now, because this yellow right over here represents our reaction, right? Basically all our stuff reacting. Now this reaction releases heat, all right? So the delta H value, remember the delta H value is negative, meaning that this reaction is exothermic, this releases heat, and if you actually put your hand, near this cup, you'll feel that the cup is very warm because this reaction is releasing heat, right? It's releasing that warmth, you feel what I'm saying? So what you have to know is that the heat, which is symbolized by Q, right? The heat that's lost by this reaction, so the Q that's basically lost by this reaction, is going to be equal to the heat that's gained by the water, right? The heat that's basically gained by water. So, because, I mean, heat doesn't just disappear, right? Heat does not just disappear, right? So when one thing loses heat, other things gain back that heat, right? So in this case, because we lost 815 kilojoules of heat, that means that my water has absorbed 815 kilojoules of heat. I mean, assuming that all the water, assuming that the heat was absorbed by the water, like all the heat was absorbed by the water. When you're doing this experiment in reality, sometimes the heat could escape, which is why sometimes you might not get your intended result, because sometimes the heat can escape through the cup, to whatever is on the outside. So that might be where the error is coming from if you're doing an experiment like this. Now, you also got to know the equation. Q is equal to mc delta T. Q is equal to mcat. Q, that's the heat symbol, right? Q represents their heat. M represents the mass. C represents the specific heat capacity. Wow, my throat is like killing me. Specific heat capacity. And delta T just represents your change in temperature. AKA, whenever you're talking about the change in something, it's usually going to be the final minus the initial. Right, so if you're trying to find a change in temperature, it's going to be the final temperature minus the initial temperature. Now, we said how this reaction is occurring in this many grams of water. We have 8.00 times 10 to the third grams. We know that the specific heat of water is 4.18 joules per gram times Celsius. All this is pretty much saying is that you're going to need 4.18 joules of energy if you want to raise 1 gram of water by 1 degree Celsius. And finally, we have our change in temperature. we know that the temperature initially started at 25 degrees Celsius, but we don't know when it ended, right? We don't know the final temperature. So remember, change in temperature, T final minus T initial. We don't know what T final is, but we do know that T initial is 25 degrees Celsius. And whoa, there's a little problem here. This is in joules, this is in kilojoules. They don't cancel out. Recall that for every 1 kilojoule that you have, that's going to be 1,000 joules. So then the kilojoules cancel out, and you're just going to be left with this many joules. So 815,000 joules. And let's just say I set both these things equal to each other. All right. So now that I have the unit for joules, the rest of this is pretty much just algebra. Right? Divide both sides by this, and then after that, add 25 degrees Celsius. And you should get the answer. So I do this plus 25. I get around 49.4 degrees Celsius as my final temperature for the water. All right, explain in terms of intermolecular forces why propanol has a significantly higher molar mass than propane, even though they have similar molar masses. Now remember, if two things have like a different molar mass, so I mean, and they're nonpolar, so remember that. If two things are nonpolar, you want to look at their molar mass. All right. So for example, if I want to compare an atom of helium in terms of their intermolecular forces to the atom of argon, recall that helium is much lighter than argon, right? It has a molar mass that's less than argon's molar mass. And this means that helium has weaker intermolecular forces, weaker IMFs than argon. And the reason why is because argon has more electrons, right? Because argon has more electrons, right? It's higher in the periodic table than helium, a neutral atom of it. That means that the electron cloud for argon is more polarizable. That's the vocabulary word for it. Another way to think about it is because argon has more electrons than helium, well, helium only has the potential to have 2 electrons on one side of the atom, right? Because helium only has 2 electrons. But argon has the potential to have way more electrons on one side of the atom, therefore creating a stronger temporary dipole, aka London dispersion force, than helium. Now, kind of the first thing that I kind of notice, the first thing that I kind of notice is that propanol, if y'all don't know, once again, all of these problems are related by this reaction. So yeah, propanol is C3H7OH. All right, think I get that right? Yep, I copied it all down. This is propanol. Now notice how this has this OH at the end, meaning that this right over here has hydrogen bonding. Hydrogen bonding is a very strong type of dipole-dipole because the difference between oxygen's electronegativity and hydrogen's electronegativity is very big. So that's going to create a very strong hydrogen bonding, very strong intermolecular force attraction between different propanol atoms. Meanwhile, propane is nonpolar. All right. Propane is going to be nonpolar because, well, carbon, hydrogen, anything that's a hydrocarbon, aka it only has hydrogen and carbon in them, they're going to be nonpolar. All right, hydrogen-carbon bonds are always nonpolar. That's what you should kind of take away from this. So because this is polar right over here and this is nonpolar, well then this is going to have a stronger sort of intermolecular force between, this is going to have a stronger IMFs, right? Stronger intermolecular kind of attractions between the molecules. Now, stronger IMFs, the higher the boiling point. So another thing to know is that the stronger the intermolecular force is, the higher the boiling point. Now, in order for something to turn from a liquid to a gas, what has to happen is that intermolecular forces between the particles has to be broken. not broken, but severely, very, very, very weakened. Pretty much to the point where it's broken. If I were to take a look at liquid water would sort of look something like this. I'm kind of too lazy. My God, this is like an awful diagram, but okay. Let's just say this is water, right? Now, water has hydrogen bonding, right? All of these water molecules are going to be attracted to each other via hydrogen bonding, right? Now, if I want to turn liquid water into gaseous water, aka water vapor, what has to happen is that I have to have enough heat in order to break or in order to weaken these intermolecular attractions, right? Now, if these intermolecular attractions are stronger, it's going to take more heat, right, in order to weaken them. So in this case, my boiling point has to increase if my IMFs get stronger. So yeah, this is propanol is going to have a higher boiling point because due to its hydrogen bond, it's going to have stronger IMFs. It's going to have hydrogen bonding. Unlike propane, which is nonpolar and only has London dispersion forces, which are weaker than hydrogen bonding.